Hey guys. So today we're going to talk about stability for discrete time systems. Just like with continuous time systems, stability for for discrete time systems is pretty much the same thing as far as the definitions are concerned. Um, so the definition for stability, if you remember what it is for continuous time systems, then you already have a leg up. Um, so the first thing for if we wanted to find asymptotic stability, we need to find two notions. We need to find attractivity and we need to define stability, right? So stability is, remember, start close, stay close, right? So namely, if we have an equilibrium point, let's say it's uh, x sub eq for equilibrium point. This point is called stable if there exists an epsilon greater than 0 and a delta greater than 0, such that if my initial condition is delta distance away, my initial condition is delta distance away from that equilibrium point, and my solution over all time, k, stays an epsilon distance away. And this is for all k in the natural numbers. All right, and then so the next notion that we need to remember is attractivity or convergence. An equilibrium point, I'll just do the same thing, is attractive or convergent if there exists a delta. Now this is going to be a local notion now. If there exists a delta greater than 0 such that we bound the initial conditions, the distance of the initial condition from that equilibrium point, and the solution or the limit of the solution as k goes to infinity is equal to that equilibrium point. All right, so now we have two notions. We have attractivity and we have stability. And these probably look, well, they should look extremely familiar because they're exactly the definitions for continuous time systems. So, and then lastly, an equilibrium point is asymptotically stable. Now this is in the local sense, right? Because we're bounding the initial conditions. If it's attractive and stable. All right, so now let's draw a picture of this. So it'll look very similar to the picture of, great. It'll look very similar to the picture of a continuous time system, although the solutions will be different, right? So we have an equilibrium point. Let's say we have an equilibrium point right there in the middle. And then we have a delta distance. This will be delta. And then we have an epsilon distance here. All right. And so now we can have multiple different types of solutions, right? We can have, if under just general nonlinear systems, we can have attractive solutions that aren't stable. We can have stable solutions that aren't attractive. We can have unstable solutions, and then we can have asymptotically stable solutions, right? So what does a unstable solution look like? Well, if we start epsilon distance or delta distance away, an unstable solution will just, oops, let's do that a little differently. If we start here at that initial condition, indicated by this red mark here, red, black mess, an unstable solution, because we're dealing with a discrete time system, right, will jump out like this, and so on. All right. Let's see, is that updating? Maybe. It's getting kind of annoying. Okay, let me refresh that. Stop mirroring. There, you guys can look at Jack. All right, now back to me. All right, so now you can see an unstable solution. Great. Jack's whining in the back. All right, so like I said, we could have multiple different types of solutions. Let's say we have a stable solution that's not attractive, right? So we start, again, epsilon distance away, and then we're jumping out like this. And remember, they're discrete points because they're the okay, it's okay. It's just a box. Good job, Jack. Sit. Sit. Shake. Okay. Up. Up. Jack. Up. It's not up. All right, I'm going to back up. All right, so like I said, we have multiple different types of solutions. We can have, I just plotted an unstable solution. We can also have a stable solution that's not attractive, right? So if we start, say, from a different initial condition, that's delta distance from the equilibrium point, a stable solution will update like this. And it'll stay inside this epsilon band. All right? So this is an unstable solution. This is a stable solution. We could have a convergent solution, right? So let's say we start again at the same point. A convergent solution can grow boundedly as long as it converges, right? Well, it can grow, and if we can't show that the solution's bounded, let's say, then we can't show stability of it, but we can still show convergence or attractivity of it. So let's say it grows out, can't show that it's bounded, but we can show that at the infinite point, it converges to the equilibrium point there. Okay, so it grows this way and then comes back this way. This could be an attractive solution. Okay, what are we missing? We're missing an asymptotically stable solution, right? All right, so again, let's pick a point in delta. An asymptotically stable solution can grow boundedly a little bit inside that epsilon ball, but due to stability, it has to stay inside that epsilon ball, right? Because global asymptotic stability requires stability and attractivity, right? And so now it'll converge at the infinite point, right? So it stays inside the epsilon ball, right? And it converges to the equilibrium point. This is an asymptotically stable solution. And lastly, we could have what's called a global asymptotic stability solution. I don't remember if I talked about this in the continuous time systems, but it holds true regardless. So a global asymptotic stability results in, remember, we're bounding for attractivity, we're bounding the initial conditions distance. This should be the delta here. So we're bounding the initial conditions of the solution. But if we remove that, we have a global attractivity result. So global attractivity with stability gives us global asymptotic stability. So that would mean that I can start a solution way out here, anywhere in the state space, and it'll converge to that origin. Great. All right, so now that we have those definitions in order, how do we show that we have asymptotic stability or attractivity, right? Because at the end of the day, we don't necessarily, we saw how to calculate solutions before in the last video, but that could be very tedious and sometimes not possible, right? For all cases of F, right, of our map. So for the let's start slow and start with just a linear time invariant system. Okay. So let's come back down here, bring my handy marker. Right. So now let's talk stability for LTI, right? So for LTI systems, for continuous time systems, we said that a system is asymptotically stable if the matrix, the state matrix A, has eigenvalues on the left half side, right? If the real component of the eigenvalue is on the left half side, we have stability, we have asymptotic stability, right? Well, there's a very similar notion for discrete time systems. Okay, and that's, so let's say we're given, let me underline this. And so if we're given an LTI, discrete time system, DTS, okay, as xk plus 1 is equal to axk, if all eigenvalues, okay, so again, it comes back to looking at the eigenvalues of the matrix A, if they're all on the unit ball, okay, so the unit ball is just a circle in the plane, in the complex plane, right, the eigenvalue plane. And so if the norm of that eigenvalue is less than or equal to 1, and we have a multiplicity of 1 for any eigenvalues on the unit circle, okay? So, and all eigenvalues, so the norm of the eigenvalues equal 1, have a multiplicity of 1. Oops, I don't want to. All right. Then this equilibrium point is what's called stable, right? So just like with a continuous time system, if you have an eigenvalue on the imaginary axis, we have a marginal stability, right? But if you have all eigenvalues on the left half side, not on the imaginary axis, then we have asymptotic stability. So the same is true here. The equilibrium point is asymptotically stable. I'm just going to say AS if and only if the norm of the eigenvalues are less than 1, right? For all eigenvalues 1 to n. Okay. And last thing I just want to note is you may hear people talking about a Shor matrix. A Shor matrix is a matrix with all of its eigenvalues less than 1. So now what does this look like? So now there is a mathematical reason behind this. I'm not going to go to the derivation of it, but like I said, we have so this will be, let's say this is a continuous time system. Do you see that? Let's make it a little bigger. Continuous time system, and then we have a discrete time system, and this is the complex plane. And both of these are LTI systems with a matrix A, right? So the continuous time system, this will be x dot is equal to AX. And then this one will be x k plus 1 is equal to AXK. Great. All right, so now, again, these are both system matrices. And this guy. Okay, so now for continuous time systems, we need that all eigenvalues are on this side, right? And then in the discrete time system, we have a unit circle with a radius of 1. Okay. Now, if all of the eigenvalues are within this unit circle, then we have stability, asymptotic stability. So those are the comparisons between them. And there is a transformation when you transform a continuous time system into a discrete time system that maps these eigenvalues. So you can show that analytically. That'll be for a graduate level course, most likely. All right. So now let's step it up a notch and look at the time varying case. So now let's look at an LTV, a linear time varying case. Okay. So namely, we're going to look at the case where we have x k plus 1 is equal to a k. So now k is changing with a is changing with k. Okay. So now we found the state transition matrix last lecture. So there's a theorem that says if the state transition matrix is bounded, so if, let's say, the equilibrium point is stable, if and only if the state transition matrix from 0 to t is bounded. So what would that translate to, right? That would translate into the solution being bounded. Next, if we can find the state transition matrix, the equilibrium point is asymptotically stable. Again, if and only if the state transition matrix from 0 to t is both bounded and converges to 0 asymptotically. As, oops, not k, this should be, not t, that should be k. All these should be k. Great. Okay, so that's how you can show stability of a linear time varying system. Again, a linear time varying system might be a system that has parameters that change during time, like as the system evolves. For instance, like a rocket loses a massive amount of mass as it goes up, right? And so you need to account for that change in mass, which adjusts where the center of gravity is of the plant of the rocket. And you need to take that into account when you design the controllers. Um, all right, now let's look at the most general form of determining stability, and that's again Lyapunov. So remember, Lyapunov is just a method to show stability. You have to find it can be kind of tricky because you may have to craft the function. To do that, it's always best to start with a quadratic function if you can. That tends to be the best starting place. But so for a Lyapunov function, uh, we want to look at the case. Let's say we want to look at the case of 0. This can be generalized, but we can say we want to look at 0 being an equilibrium point. Or just the general nonlinear function, where the most loose version is where f is locally Lipschitz. And then suppose there exists a function v which is continuous and maps to the reals. This should be Rn to R. All right, so this is such that, again, we have V0 is equal to 0, just like for the continuous case. And we have positive definiteness, positive semi-definiteness for all x in the state space. And then we have positive definiteness for all x not equal to that equilibrium point, not equal to 0. Okay. And then if we can show, remember with the continuous time systems, if we could show the derivative of v was decrescent for all x, then we could show asymptotic stability. And if it has areas where you have a it's equal to 0, the derivative of v, then you have just stability. The same is true with this, just different. So you have the change in v, right? Because we're not dealing with a continuous system anymore. We're going to look at the difference between the mapping of the system and the state. Okay, and we want this to be less than or equal to 0 for all x. If this is true, then the equilibrium point 0 is just stable. And if we can say that the difference between v after the mapping and before the mapping is strictly decreasing for all x not equal to 0, then x equals to 0 is asymptotically stable. So that's pretty cool. So, but and note that it's very similar to what we saw with continuous time systems. With continuous time systems, we looked at the case where we have x x dot equal to f of x, right? And then these all hold true. These all hold true until we get to this guy right here, right? And we looked at the case where v dot of x is less than or equal to 0 for all x. Then we get stability. And then if we have that v dot of x is strictly less than 0 for all x not equal to the equilibrium point, then we get asymptotic stability. Looks weird. Erase that. So yeah, so it's very similar. So then the last thing I wanted to talk about is using Lyapunov theory for linear time invariant systems. Kind of following the same stepping process that I did for continuous time systems. So let's look at Lyapunov for LTI. All right, so let's do that. All right, so now the problem is, given a system, x plus or x of k plus 1 is equal to a times x k, and assume there exist two matrices, P equal to P transpose, positive definite, and Q equal to Q transpose, positive semi-definite, such that this expression is true, okay? So now either find Q or find P by setting one or the other. Then the origin is asymptotically stable. Okay, so now to show this, let's look at a quadratic equation. Okay, quadratic Lyapunov function. Okay, so now remember P is positive semi-definite or positive definite, PD. Okay, so since P is positive definite, well, for one, we know that V0 is equal to 0, right? If we take x equal to 0, V 0 transpose P0 is equal to 0. Right? We know that for all x, since P is positive definite, that this is greater than 0 for all x not equal to 0, right? And then the last thing we need to show is that the difference minus is equal to v of a x minus v of x, right? We need to show that this is decreasing. So let's do that. So v of ax, remember ax is equal to, v is equal to x transpose p times x. So that means that this is ax transpose p ax minus x transpose px. Then we get x transpose a transpose p a x minus x transpose px. All right, you guys seeing where this is going? We get x a transpose pa minus p times x. Okay. Now remember our assumption, right? Let's go back. We assumed this guy down here, right? We assumed that A transpose PA minus P is equal to negative Q, where Q is positive semi-definite. So coming back over here, we know that this will be equal to x negative x transpose Q x, which is less than or equal to negative minimum eigenvalue of Q times the norm of x squared. So we have that for all x not equal to 0, we have a strictly decreasing function, right? We have that the eigenvalues of Q are, let's say we pick, are negative. We have that, or even if they're 0, we still have that they're less than or equal to 0 or less than 0, right? And then, right, so then it just remains to find that P and Q that guarantee this. So you just need to solve A transpose PA minus P is equal to negative Q. And it turns out that if you can solve this, it shows that all the eigenvalues are less than 1. And it's a bidirectional equivalence here. All right, that's all I wanted to talk about for discrete time systems. I just kind of want to give you an overview of the system. They are they're pretty powerful, especially if you have a slower moving systems or your samples, your step sizes between your samples are slow. If you have a faster sample size or sample rate, you can pretty much do everything in continuous time systems using a controller, a discrete controller, like a computer, because they're so fast. I didn't have many specific examples on this, but I just wanted you to know the basic concepts of it. A high level question might show up on the final, and just a conceptual question. So great, thanks. Last lecture will be on Thursday. I will just give a synopsis of the class after the midterm. The final will be on all the material after that midterm. I'll post something in Discord to make sure that everybody's on the same page if they're not watching the videos. That's all I got. Thanks.